All right, let's talk about one of the most fundamental, and let's be honest, one of the most misunderstood concepts in all of software, sockets. Our goal today, we're going to completely demystify them for you.
So let's kick things off with a pretty bold claim, right? 99% of developers don't get sockets. Now, is that an exaggeration? Yeah, maybe a little. But, it gets at a real truth. Sockets are one of those core concepts that, well, even for seasoned pros, our understanding can be a little fuzzy.
And hey, it's not just sockets, is it? They're kind of in this club of concepts, things like file descriptors or ephemeral ports that just feel like this amorphous, hand-wavy construct in our heads. We know they exist, we know they're important, but the details, a little blurry.
So that's our mission for this explainer. It's really simple. We're going to take all that confusion, all that fuzziness, and swap it out for a solid, concrete mental model. You're going to walk away knowing what sockets are, how they work, and, most importantly, why they're just so absolutely essential.
Okay, so let's get right down to it. Let's strip away all the jargon and ask the basic question. What exactly is a socket?
Well, at its very core, a socket is just a software thing, an abstraction. It's not physical hardware. Think of it like a doorway. The operating system creates this doorway, and it's what lets two different programs have a conversation. It doesn't matter if they're on the same computer or literally halfway across the world.
And the best way to get this is the classic telephone analogy. Seriously, it's perfect. The socket, that's the phone itself, the actual device. The IP address, that's the phone number for the entire building. And the port, well, that's the specific extension you need to dial to reach the right person. You absolutely need all three to make the connection. Now, for those of you who think in terms of network layers, here's where sockets slot in. They live right at layer 4, the transport layer. They're basically this crucial bridge connecting your application, say your web browser up at layer 7, down to all the complex networking machinery that's actually routing and sending the bits and bytes.
Okay, theory's great, but now let's see how these things actually work in the real world. Let's get into the action.
So, sockets really come in two main flavors. First, you've got TCP, and the phone call analogy still works here. It's connection-oriented. You establish a solid line, and you get a guarantee that everything you send arrives, and it arrives in the right order. This is perfect for stuff like web browsing or downloading a file. You can't have missing pieces, right? And then, on the other side, you've got UDP. This is more like sending a postcard. It's super fast, very lightweight, but there's no guarantee it'll get there or in what order. This is awesome for things like video streaming or online gaming, where dropping a single frame is way better than lagging. All right, let's put ourselves in the shoes of a server. It's a very specific dance it has to do. First, it creates a special listening socket. Then, it binds it to a specific IP and port, basically saying, this is my address, I'm open for business right here. Then, it listens. It waits for someone to knock. When a client finally connects, the server accepts. And here's the magic trick. It creates a brand new, dedicated socket just for that one client. The original listening socket, it just goes right back to listening for the next connection. Finally, the server communicates with the client on that new socket. This whole process is how a single server can juggle thousands of clients all at once.
Now the client side, way simpler. The client just creates a socket and says, hey, connect me to that server's IP and port. But here's a really cool detail, especially on systems like Linux or Mac OS. The operating system treats that socket connection just like a file. It gives it something called a file descriptor, which is really just a number, a unique ID. And what that means is a program can write data to the network using the exact same simple commands it would use to write to a text file on your computer. It's a beautiful piece of abstraction.
So have you ever wondered how your computer can have, say, two browser tabs open to the exact same website at the same time? How does it keep those conversations separate? The answer is this thing called the 5-tuple. The OS tracks every single connection using a unique combination of 5 things: the protocol, your source IP, a unique source port, the destination IP, and the destination port. Look at the table here. Even though the destination is identical, the OS gives each connection its own source port, 54.123 for one, 54.124 for the other. That little difference is what makes each connection totally unique.
Okay, so we've got the fundamentals down. Now let's level up and look at a couple of concepts that are absolutely critical if you're building modern, high-performance systems.
So the old school, simple way to handle connections was one thread per socket. But think about it. That's like having one dedicated cashier for every single customer in a huge supermarket. It just doesn't scale. You run out of cashiers fast. The modern solution is something called non-blocking I/O. This is the magic behind things like Nginx. Instead of one thread waiting around for one socket to do something, a single thread can manage thousands of them. It basically tells the OS, hey, don't bother me. Just let me know when any of these thousands of sockets has data for me. It's unbelievably efficient because that thread is never, ever just sitting around waiting.
But wait, not all sockets even need to go over a network. What if two programs on the exact same machine need to talk to each other? Well, for that, they can use a Unix domain socket. Instead of using an IP address and a port, it just uses a file path on the local system. The benefit? It's way faster because it gets to completely bypass the entire network stack. This is a big reason why connecting to a local database like PostgreSQL on your own machine feels so incredibly snappy.
Okay, this next point is absolutely critical. We have to talk about security. By default, raw sockets are completely insecure. They send data in plain text. That means anyone snooping on the network can read everything. That's why you have to, and I mean have to, wrap your socket communication in a security layer like TLS, Transport Layer Security. That's the S in HTTPS. It's what takes your plain text data and turns it into an encrypted, unreadable lockbox that only the intended recipient can open.
All right, we've been deep in the weeds, looking at the mechanics. Let's zoom all the way out now. Let's connect all of this back to why this stuff really matters to you as a developer.
Just think for a second about the tools we use every single day. REST APIs and gRPC? Yep. Load balancers like Nginx and Envoy? Service meshes, message queues like Kafka, databases like Postgres and Redis? What do they all have in common? They are all built on the invisible foundation of sockets. They are the absolute bedrock of modern network software.
And this isn't some obscure academic detail, right? This is happening constantly all around you right now. Every time you load a web page, send an email, use a mobile app, every single one of those actions is powered by countless sockets firing off and communicating silently in the background.
And that is why understanding them is so powerful. It's not just trivia. It's like a superpower. It gives you the ability to build better, faster, more resilient systems. It lets you debug those really tricky network issues that stump everyone else. Truly getting sockets isn't just knowledge, it's a major professional asset.
So, there you have it. We've laid out the foundation. Sockets are the fundamental building block, the Lego brick of all network communication. So the only question left for you is, what are you going to build on it?